The other interesting reaction of acid chlorides is their conversion into esters. Let's draw a general scheme for that reaction, and then we will see how we can postulate a mechanism for that nucleophilic acyl substitution reaction. So this is a general structure for an acid chloride. The acid chloride is then treated with an alcohol, ROH, whose general structure is ROH, in the presence of pyridine, as we have seen in general scheme of reactions of acid halides. So alcohol, pyridine on acid chlorides. Now this reaction gives the corresponding ester. So it is an esterification reaction. Of course, this esterification reaction is a very useful one in addition to the esterification methods that we have learned before. And of course, as we have learned before, carboxylic acid can be esterified using the Fischer esterification method. That's if the carboxylic acid is treated with an alcohol in the presence of an acid catalyst. So that's one method for the esterification of carboxylic acid. The other method is if the carboxylic acid is initially converted into the corresponding carboxylate ion, and then subsequently the carboxylate ion is treated with an alkyl halide to form the corresponding ester. Now, those were direct esterification methods of carboxylic acids. Now, this is an esterification reaction of acid chlorides. That if the acid chloride is treated with an alcohol in the presence of pyridine. Now, pyridine is a heterocyclic compound. It's a 6-member heterocycle containing nitrogen. Let's draw the structure of pyridine. This is pyridine. It's a 6-membered heterocycle. That lone pair is available for donation. It is not delocalized inside the pi system. So therefore, pyridine is actually basic because this lone pair is available. So one possible mechanism for this reaction is for pyridine to attack the acid chloride initially in nucleophilic acyl substitution reaction. So let's do that. We take an arrow from the lone pair on nitrogen in the imine unit of pyridine. So nitrogen attacks, if you like, carbon of the acid, carbon of the carbonyl group of the acid chloride. This double bond is broken. It's reformed, and the CCl bond is simultaneously broken. The product that's obtained is, or the intermediate that's obtained is actually this one. This intermediate where nitrogen of pyridine has a positive charge. It's like a pyridinium ion in a way. If you notice, the alcohol has not taken part yet. So the alcohol can now come and does a nucleophilic acyl substitution type on this intermediate, which is formed as a result of the attack of pyridine on the original acid chloride. Now, this acts as an excellent leaving group, and it is because nitrogen has a positive charge. So the alcohol will now come. The alcohol comes in and does nucleophilic acyl substitution type. It attacks carbon of the carbonyl group. The carbon-oxygen double bond is broken. It's reformed with the departure of pyridine. So it's actually reformed. So pyridine was used initially, and now it will be reformed. So what we get is this intermediate plus pyridine reformed, and therefore it can also be reused. So a conjugate base can actually come in now and take off that hydrogen, for example, Cl minus. A chloride ion can come in and take off that hydrogen from this protonated intermediate to give the final ester product. Now that pyridine is reformed. It can then be recycled. It is reformed, it can be recycled. So it acts in a way as a catalyst, but also it's a nucleophile at the same time, because it does this nucleophilic acyl substitution step. It is a nucleophilic acyl substitution, and obviously this one is also a nucleophilic acyl substitution step. So pyridine acts as a nucleophile. It does a nucleophilic acyl substitution reaction on the acid chloride. So it is used, and here it is reformed, and then it can also be reused. So in a way, it's also a catalyst, and it is a catalyst. Specifically, it is a nucleophilic catalyst. So the role of pyridine in this reaction is actually a nucleophilic catalyst. It's a nucleophilic because, again, it acts as a nucleophile in the initial nucleophilic acyl substitution step. It is a catalyst because it is a substance that's used, reformed, and thus reused or recycled. So its role is actually a nucleophilic catalyst. So again, this esterification reaction is a very useful reaction for transforming an acid chloride into the corresponding ester if the acid chloride is treated with an alcohol in the presence of a nucleophilic catalyst such as pyridine. And on this note, by the way, it's not just pyridine that can be used as a nucleophilic catalyst. Other heterocycles can also be used, something like imidazole. This is imidazole. Imidazole can be used as a nucleophilic catalyst as well. And another pyridine compound can also be used, and that is DMAP, or dimethyl amino pyridine, 4-dimethyl amino pyridine, NN, or 4-NN dimethyl amino pyridine. It's abbreviated as DMAP. So DMAP and imidazole can also be used as a nucleophilic catalyst in the transformation reaction of acid chlorides into esters. So again, in summary, this is a very, very useful reaction for making esters from acid chlorides by reacting the acid chloride with an alcohol in the presence of a nucleophilic catalyst.